Right. Today we are going to discuss about boundary layer thickness. What is boundary layer thickness? What are the types of boundary layer thicknesses? Right now we are going to discuss about boundary layer thickness. What is the definition of the boundary layer thickness? It is defined as the distance from the boundary of the solid body measured in y direction to a point where the velocity of flow is approximately equal to 0.99 times the free stream velocity. Right here, this is the boundary layer. This is the boundary layer. Is the distance measured perpendicular to the boundary. The velocity over the boundary is 0. Away from the boundary, the velocity gradually increases. At one point, the flow in this region reaches to the free stream velocity. That means that is 0.99 times the free stream velocity, that is known as boundary layer thickness. Right now, the boundary layer thickness is denoted by delta. The boundary layer thickness is denoted by delta. Right. The boundary layer thickness along the length of the boundary, along the length of the channel, classified into three layers. One is laminar boundary layer, transition zone, and turbulent boundary layer. Right here, this is the boundary. This zone is known as laminar zone. This zone is known as laminar zone, and this thickness is known as laminar boundary layer thickness. This thickness is known as laminar boundary layer thickness. This is denoted by delta laminar, that is the thickness of laminar boundary layer. Whereas the thickness of transition zone, this is the thickness of transition zone, this is the transition zone, this is the transition zone, this is denoted by delta star, thickness of the laminar sublayer. Then this is the thickness of the turbulent zone. This is the turbulent zone. This is the turbulent zone. This is the thickness of the turbulent boundary layer. Okay, this is denoted by delta turbulent equal to is the thickness of the turbulent boundary layer, and delta star is the thickness of the laminar sublayer. This is the laminar sublayer. Laminar sublayer is part of turbulent laminar zone. Right, that already I have explained to you. Definition of displacement thickness, definition of momentum thickness, and definition of energy thickness. Right, what is the purpose of these thicknesses we have introduced here? If the water is flowing over the solid body, if the water or liquid is flowing over the solid body, there is a formation of boundary layer thickness. This is the boundary layer thickness. Because of the formation of the boundary layer, this is the boundary layer, this is the solid body. Because of the formation of the boundary layer, there is a reduction in rate of flow. Because of the boundary layer here, the water is, this is the free stream velocity capital U. The liquid is flowing over the boundary layer. The liquid is flowing over the boundary layer. This is the shape of the boundary layer. Because of the boundary layer formation, there is a loss in the rate of flow. To compensate this loss in the rate of flow, the boundary layer thickness is displaced to a distance delta star. This delta star is known as displacement thickness. Okay, once again, I am going to give the definition of the displacement thickness. It is defined as the distance measured perpendicular to the solid body by which the boundary layer is displaced to compensate for the reduction in the rate of flow, reduction in the rate of flowing fluid, and account of boundary layer formation. An account of boundary layer formation, this is known as displacement thickness. Right here, already I have explained, this is the solid body Once the water having free stream velocity u, this is flowing over the solid body, automatically here we are having the boundary layer. Because of the boundary layer formation, there is a reduction in the rate of flow. This u, this is having some q is equal to av. Q is equal to av. Velocity, this is the free stream velocity, but within the boundary layer this is not equal to free stream velocity. That velocity is gradually reaches to free stream velocity at the top, but here velocity is less, automatically rate of flow is reduces. To compensate this rate of flow, this boundary layer is displaced to a distance delta star. Delta star, this delta star is known as displacement thickness. Okay, momentum thickness. Here also, when the liquid is flowing over the solid body, there is a boundary layer formation. Because of the boundary layer formation, there is a reduction in the momentum of the flowing fluid. To compensate this momentum of the flowing fluid, that boundary layer is, this is the boundary layer, is displaced to a distance theta. This theta is known as momentum thickness. Once again, definition of the momentum thickness: it is defined as the distance measured perpendicular to the boundary by which the boundary layer is displaced to compensate for the reduction in the momentum of flowing fluid on account of boundary layer formation. Here also, as like as earlier case, once the liquid is flowing over the solid body, there is a formation of boundary layer here. Because of this boundary layer, there is a reduction in the momentum of the flowing fluid. To compensate this reduction of the momentum of the flowing fluid because of formation of boundary layer, that this boundary layer is displaced to a distance of theta. This is known as momentum thickness. Right? Next one, energy thickness. This is also same case. It is defined as the distance measured perpendicular to the boundary by which the boundary layer is displaced to compensate for the on account of boundary layer formation. Here also same system. The water is flowing over the solid body. The liquid is flowing over the solid body. There is a formation of boundary layer. Because of the boundary layer formation, there is a reduction in the kinetic energy. To compensate this reduction in the kinetic energy, the boundary layer displaced to a distance of delta double star. This is known as energy thickness. Okay, the displacement thickness is denoted by delta star. The momentum thickness is denoted by theta, and energy thickness is denoted by delta double star. Right? Now we are going to solve some problems related to displacement thickness, momentum thickness, and energy thickness. Right? This is the first problem. Find the displacement thickness, momentum thickness, energy thickness for a velocity distribution in a boundary layer given by u, small u by capital U is equal to y by delta, where u is the velocity at a distance y from the plate, and u equal to capital U at y is equal to delta, where delta is the boundary layer thickness. Also calculate the value of delta star by theta. Right? You have idea about boundary layer thickness. Suppose this is the solid body, this is the free stream velocity u. Right? So over the solid body, the velocity is 0, perpendicular to the plate. The velocity gradually improves at one location. The velocity perpendicular to the solid body gradually increases at one location. The velocity reaches to the free stream velocity. The velocity reaches to the free stream velocity. The velocity at 0, that y is equal to, velocity is equal to 0, and at y is equal to at y is equal to theta, velocity equal to capital U. That means at y is equal to 0, this is the point. At y is equal to theta, this is the point. The velocity is equal to capital U. This is known as displacement thickness. Right? This is known as displacement thickness. They have given the ratio or the relation between small u by capital U equal to y by delta. Small u by capital U is equal to y by delta. Now we are going to determine the displacement thickness, momentum thickness and energy thickness. Right? What is the formula for the displacement thickness? Displacement thickness delta star equal to integral 0 to delta 1 minus small u by capital U dy. This formula already I have explained in the last class. Right? Now small u by capital U, small u by capital U equal to, they have given relation that is equal to y by delta. Right? Now in place of small u by capital U, we are going to substitute y by delta. Therefore delta star, this is the displacement thickness, equal to 0 to delta 1 minus, in place of small u by capital U, we are going to take y by delta dy. Delta star is equal to 0 to delta 1 minus y by delta dy. Now this is integrate with respect to y. Therefore with respect to y, this is equal to y minus y square by 2 delta and the limits 0 to delta. Now apply the limits 0 to delta. Therefore in place of y, we are going to take the delta, delta minus delta square divided by 2 delta. Right? Now square delta gets cancelled. This is equal to delta minus delta by 2. This is equal to delta by 2. This is the displacement thickness. Displacement thickness is equal to delta by 2. It indicates that the displacement thickness is half of the boundary layer thickness. Right? This is about displacement thickness. And another one, momentum thickness. Momentum thickness, what is the formula? Momentum thickness is denoted by theta. Theta equal to integral 0 to delta small u by capital U 1 minus small u by capital U dy. This is the formula for the determination of momentum thickness. This is already I have derived in the last class. Right? Here also in place of u by capital U, we are going to substitute the y by theta. Right? Therefore theta equal to, or momentum thickness is equal to integral 0 to delta. In place of small u by capital U, we are going to take y by theta, y divided by delta, bracket begin, 1 minus y divided by delta dy. This is equal to integral 0 to delta y by delta multiplied with 1, y by delta minus y by delta multiplied with y by delta, that is equal to y square divided by delta square into dy. Now this is integrate with respect to y. We have theta equal to y square by 2 delta minus y cube by 3 delta square and the limits 0 to delta. Now we are going to substitute apply the limits. This is equal to delta square divided by 2 delta minus delta cube divided by 3 delta square. Right? Delta square gets cancelled. Delta square, this is cube cancel. This is equal to delta by 2 minus delta by 3. Now this is equal to 6. This is equal to, right, this is equal to 3 delta minus 2 delta, this is equal to delta by 6. Now the momentum thickness, theta equal to delta by 6. Momentum thickness is equal to displacement thickness divided by 6. Next, right, energy thickness is denoted by delta double star equal to 0 to delta small u by capital U 1 minus small u square by capital U square dy. This is the formula already I have explained, derived in the last class. Right, small u by capital U is nothing but y by delta. Right, this value is substitute here. This is equal to 0 to delta. Right, y by delta bracket begin 1 minus y square by delta square dy. Right, this is equal to y by delta multiplied with 1 and y by delta multiplied with y square by delta square. This is equal to integral 0 to delta y by delta minus y cube by delta cube into dy. Now this is differentiate with respect to y and apply the limits 0 to delta. This is equal to y by delta, that is y square by 2 delta minus y power 4 by 4 delta cube, and also apply the limits 0 to delta. This is equal to, apply limits here 0 to delta, therefore delta square divided by 2 delta minus delta power 4 divided by 4 delta cube. Right, delta square cancel, cube 4 cancel. This is equal to delta by 2 minus delta by 4. This is equal to 4. Right, 2 delta minus delta, this is equal to delta by 4. Therefore displacement thickness, energy thickness double star is equal to delta by 4. The energy thickness is displacement thickness divided by 4. Right, one more point here they have asked, that is what is the ratio between the displacement thickness and momentum thickness. Displacement thickness delta star divided by momentum thickness. What is the displacement thickness? That is delta by 2 divided by, what is the momentum thickness? That is already we have determined, that is equal to delta by 6. This is equal to delta by 2 into 6 by delta, delta gets cancelled, 4. This is equal to 4. Displacement thickness by momentum thickness is equal to 4. This is the relation between the displacement thickness and momentum thickness. Right, thank you one and all.